when the people at uh, the Department of Commerce, which is over NOAA, who were supporting my work, retired, the people at NOAA came to me and said, "Don't you know the government is not about saving money or being efficient and doing
Yeah.
work? The government is all about money." And they said to me, "Each of those computer centers that you replaced, we didn't need a computer center building anymore. We put your computer in a closet and locked the door, and that was fine. Um, we didn't need all the employees that we had there to help run the computers, because yours could be easily handled by one person, and uh, and we didn't have to give out contracts that often went into the billions of dollars for maintaining that computer center. And the kickbacks on those contracts were millions of dollars a year per computer center. And
No
the
doubt.
people who used to get those aren't getting them anymore, and they hate you, and they want us to get rid of you as quick as possible. And so
Nice.
they said, if you don't leave today, you're fired. So I went to the Census Bureau, which is also under Commerce, but not is not part of NOAA. And they said, "We love all the stuff you can do, but we don't want to use your computers." And so,
How
uh,
long were you at Noah?
um, probably about 15 years.
They're my mortal enemy.
Oh, really?
They're one of the foundational pushers of climate alarmism, and I'm heavily opposed to climate alarmism.
Uh-huh.
Intend to prove it wrong. That's the whole reason I got into physics, was to prove climate alarmism is unfounded.
Uh-huh. Well, my work in on the universal force, I found that uh, we are currently under what's called the postmodern philosophy of science, which has a separate silo for each area of science. So, for
Yes.
instance, the chemists discovered in chemical laboratories that the force of gravity is electromagnetic in origin. Well, the physicists didn't want any of that stuff to be put in their journal. So they made their silo with their journals such that they could control what was published there. And that's what they did. And so, but I found that they had already discovered that. And so I was able to do work from electrodynamics. We had a problem in electrodynamics also. There were 6 empirical equations of electrodynamics, Gauss's laws, Faraday's law, Ampere's law, Lenz's law, and Lorentz's law. And those 6 equations had 8 unknowns. And if you use the Galilean transformation, that gave you all 8. And if you solved it, uh, you discovered they solved all 8 equations together. You obtained a very nice solution. You don't need relativity theory. You don't need quantum mechanics. Uh, and you can explain much more data. And then I found you could derive the force of gravity. Force of gravity is due to oscillations between basically the electrons and the protons in um, atoms. And it it is the only electromagnetic force that cannot be shielded. The other types of electromagnetic force that don't involve these oscillations can be shielded. And so when you drive that, and you get a value of big G, and you also don't need dark matter and dark energy, because it now explains all that phenomena. And so that was very interesting. And you get what's called a modified Newtonian dynamics, MOND. And we've verified that. NASA has verified that in our solar system by showing that the force of gravity does not agree with general relativity theory or Newton's universal law of gravitation as you go out from the sun toward the edge of our solar system. So it's been quite an interesting time. And one of my contributions to computer science, and I did a lot of stuff in computers, but one was how to eliminate round-off error in your calculations. And many people, particularly those who work with accelerators and stuff like that, they never knew how to do that. So their results are interpreted incorrectly. And I was able to show how to do that. And I advised many theses, honors theses, at the College of William and Mary when they got published results in various journals related to that in particular problems in science. And so anyway, we have a lot in common, and also we have worked with a variety of different problems, and I think that's very interesting. And an organization like ours, you can meet and talk to a number of people who have a different perspective. But what I find is the most successful people who have a different perspective, they can see things in one way, in a certain aspect of it, and they can point out very interesting features. And then if you take your own work, you realize, oh, I could explain that the same kind of way, but from a different perspective. But there's things in common. Like, just to give you an example, in quantum mechanics, you have a universal wave function. And that is very similar to the work that I do, where you don't have a universal wave function. What you have is the electromagnetic field. And the field is everywhere, and the field has tensile strength, and it has certain properties, and it can predict everything that quantum mechanics was designed to predict, but it predicts it better. And for instance, when you do a theory of the atom, it predicts all of the emission, absorption, and spectral lines in hydrogen and helium. But no other theory of the atom can predict a single emission spectral line in extreme ultraviolet. And it turns out there are just as many spectral lines in the extreme ultraviolet as all the other spectral areas for hydrogen and helium. So the current theories can only, at best, do 50% of the properties of a hydrogen and helium atom. And so that's a significant thing. But I first learned about that when NASA did an experiment in space, and they put a rocket on the dark side of the Earth, pointing away from the Earth, and of course the sun was behind the Earth, and they opened the rocket door to the light coming in from the darkest parts of the universe that they could see, and then they used grating, and they split it up into spectrum lines, and they got all these lines in the extreme ultraviolet. And on Earth, you can't see a single line in the extreme ultraviolet, because if you have hydrogen or helium, and it's a gas, and you have to put it in some kind of container, like a glass container or whatever, and it absorbs all the extreme ultraviolet, so you never see it. And so that was interesting to have that done. And my second oldest son, who went to a science and tech high school, and he had to have a science fair project, a significant science fair project, he did one on a new theory of the atom, and he won the grand prize at the International Science Fair, and that was worth about $400,000. So it paid for his college education, at least. And but you know, there's just a lot of things that are in our backgrounds I find that are common. I think we probably get energized by similar types of developments. Let's see. We have Franklin, who is here. Do you want to say something, Franklin?
Yeah, I was just listening to your accomplishments there. I was wondering, is there any information on the internet about your super micro or was that many years ago? So long ago that because you said that a company produced them. Like, what was the name of the company, and are they still in business?
It's called Micromation, and the company expanded so fast with these computers that there was a change in the value of the currencies around the world, and it caused them to go bankrupt because they had loaned out so much money to people to buy these computers all around the world, and they couldn't pay it off because the value of the currencies which were given in the contracts changed, and there was no way they could make it work. And they were new at that. They started out as a arcade game company, making arcade games to go in airports.
How did you spell the name? I was just curious. I'm going to Google it and see.
Micro Mation, M-A-T-I-O-N, all one word.
M-A...
Micro, M-I-C-R-O-M-A-T-I-O-N.
I-O-N, Micromation.
All one
Let's see what the internet has to say about Micromation. Let's see here.
And my computers, by the way, are still in use after 40 years at NIST, because there is no other computer in the world that can receive all this satellite data coming down at gigabit rates. One of my computers, just one, is able to receive millions of times more data per second than the current computers. So they're still using it, but it's.
Well, I'm wondering. So I found this wiki page. I'm wondering, is this Micromation founded in 1977 by Ben Cooper?
Yeah. Now they made primarily arcade game computers, but they were multiple processor computers, and I was able to design a new motherboard for one of their computers, and I was able to make it such a way that I could put 32 satellite CPU cards plugged into the motherboard with the S100 bus. And so that was how I got all those computers in there. And then in order to make the computers faster, because computers, even the ones I was using, the CPUs made in Great Britain. We didn't make this kind in the United States. It was an 80-bit CPU, and they used 80 bits instead of 64 bits, which we now use. But because they had to correct the memory of the CPU and also the regular RAM memory for cosmic radiation. We didn't know how to make the memory chips so they would not be affected by cosmic rays coming in and flip the bits. And so they had these extra bits, and what would happen is that when a bit was changed, the check bits in the extra 16 bits were used to find out what bits should have been, and then they just corrected on the fly. And so by doing that, they were able to keep the computer running. And today we don't need that. We have better chips. But I also wrote what's called a stack-oriented operating system. That is an operating system that runs just in the memory of the CPU, not the RAM of the computer, the CPU chip. And it's very efficient. It's 7 times more efficient than assembly language and 50 times more efficient than C, which is what the language that most of the operating systems today are written in. So you get a an advantage of a factor of 50 there. And then I wrote 52 data compression algorithms, which I applied to the RAM of the computer. And RAM was very small in those days. And I was able to get, for the kind of work we did in the government, I was able to get a minimum of a 40-to-1 compression ratio. So that means that I could read and write to memory up to 37 times faster, but I had 40 times as much memory. And I could do the same thing. I could apply that to tape drives, and I could apply it to hard disk drive. And so I did. And so my computer was the first one to have a petabyte computer. A petabyte is 1,000 terabytes.
I was wondering, is there a name of your computer that we might search for? Did it have a specific name?
Well, it was called the Micromation computer.
The whole computer was called Micromation.
Yes. And Micromation also made arcade games. So if you would go to the places that had arcade games where you put in your money and you play a game, you would see some with their name on it. But these were not my computers. That was their computer. And they picked up my computer and they sold it to the government for $8,000 at my request. And it was replacing billions of dollars of computers in computer centers for $8,000. Now you can see why some of the people at NOAA were unhappy because I reduced the cost of high-powered computers so much that they couldn't get big kickbacks on all the contracts. And of course, in the Washington area, government's all about kickbacks. I mean, every member of Congress gets it. Every person who approves contracts in the government gets it, and they all look forward to it. And there's many thousands of people who get those. So, but I was too idealistic. I didn't know all that when I first started out. I thought the government was all about serving us instead of serving themselves. But that's what you learn over time.
I'm just looking up some of these things here.
Yeah.
Like an old electronics magazine here. 1980. I think they had something about.
Yeah, and my computer had the first modem card in it of any computer that you could just plug a telephone line into. And I wrote the software with a fellow from IBM in Chicago. And we did the first bulletin board systems, which we call today websites. But when we were just using, we didn't have a internet in those days. We just used telephone lines. And we were able to do a very high baud rate on the telephone line, 56K baud rate and higher on standard telephone line. And the modem card was designed and developed between myself and another person here in the Washington area, and it was called Potomac Micromagic Incorporated. And we did the first cities that were governed online on the telephone line, and you participated. Everyone was required to participate in local government. You had to be on various committees and attend meetings and give your input and do your work and all that kind of stuff, all online with your telephone line and using a TV. And you made a little gadget that would go on your TV that would enable you to do all this type of activity. And
this is fun here. I'm looking at this old magazine here. It looks like you can actually search by word. They've apparently scanned in the entire thing and mapped every single word here. So I seem to have found an advertisement for some of Micromation's products here. So I guess they have a computer here called sorcerers and S100, a micromation megabox, 1.1 megabyte capacity, power supply case disk controller, and for $2,869.
Yeah, but that was a long time ago. And see the S100 boards? I use an S100 board in my computer.
Yeah, that's how you connect together all these motherboards. So, but I would presume that that computer was not available. The other article said that was mostly for governmental use, but apparently this is what they had for public consumption.
Yeah,
but that's interesting. Yeah, we can back up your story here, since a lot of what you say kind of sounds really fantastic. But no, we can go and look at available references on the internet. Say, yeah, there was a company doing that, and with S100 buses, and sold to the government. So.
Yeah, and by the way, many companies like Microsoft, Apple, and even IBM, when this company Micromation went bankrupt, they got the people and brought them to their sites and got them to help them develop more capable computers. And but at one time in NOAA, over 500 computer centers were based on these computers. And on our S100 bus, we had 32 slots, basically, and each one had what we would call a whole computer on like a motherboard, or two computers actually on the motherboard that would plug into that. So you had 32 dual processor boards that would go in that computer. And
well, the reference said to use the Intel and Zilog processors.
Well, at first we used from Great Britain, but yeah, Great Britain saw what was being done. You know, IBM was founded by the people who worked at the Census Bureau, at U.S. Census Bureau. They started out with cards, and they were reading cards, and the card would be punched with the information on each party that they were collecting data on, whether citizens or whatever. And then you could run it through a machine, and it would give you totals and things like that. The people who were working at the Census Bureau said, oh, this is really promising. We ought to do this separate from just the Census Bureau. So they founded IBM. And IBM started out with just card punches and card readers and printers that could print a report summing up the information on the cards. And then they, working with the military, they got the first vacuum tube computers built, and they wrote an operating system for that. And then when the British saw that the potential there, they decided that they would leapfrog ahead of us and go for solid state CPUs, and the government did the work to design and got the manufacturing of these started, but they didn't do operating systems and all the other circuitry required to make them into a computer. So I was actually the first person who did that. And I had been a photographer as an undergraduate at the College of William and Mary, where I used the what do you call it? Place where you develop your film and everything. Anyway, I used the darkroom. I was used to doing all kinds of things there. And so I was able to design a printed circuit board and print it on a copper sheet. And then I was able to solder in all these new CPU chips and other support chips and build the computer. So I built the first handful of them, and they were at the Space Radiation Effects Laboratory. And then after I got my PhD and started working in other places, the need for more of those came about. So I worked with this company, Micronation, and got them to make to manufacture on a major basis these other computers, and that's what caused them to grow so rapidly. But they were a small company to start with, and when they started doing contracts that were in the billions of dollars, they got lost, I guess you're saying. I wasn't an expert in international trade and tariff and all that kind of stuff, and my father was, but interestingly, but I wasn't. And my father, by the way, because he was the world expert on international trade and tariff, he was asked to negotiate the creation of the European Union and to write the contract in the 1960s that created the European Union. And he did that. And there were 9 nations to start with, but the European Union was so successful in terms of trade and tariff that the number grew to 29 very quickly. And but then the second phase was to have a common currency, and not everybody agreed with that. And the third phase was to give up some of your sovereignty. My father wasn't involved in the second and third phase, but the first phase he was, and that was the most successful phase of the European Union. So that's a little bit of my background in that area. And
now you were saying something about IBM here, and like IBM goes like way back, like the 1880s. That's like way before any of us, right?
Well, but IBM, you see, was using card readers and punches. And look here, it says right at the bottom of this page, next to the part in blue, that was first applied and drew on his work at the U.S. Census Bureau from 1879 to 82. So you see, the Census Bureau is the one that really was created. And they came up with this idea of card readers and card punches and stuff like that. And by the way, when I first started working at NASA, they were still doing that, and they had vacuum tube computers. And I worked at Building 1. If you go into the NASA Goddard Space Flight Center here in the Washington area, and Building 1, which is on your left as you go in the main gate, that is where they had their big vacuum tube computers. And I actually did some work on those computers at one time. And NASA was having trouble. They were losing track of their satellites. And the reason was that the programs they had that they used to calculate the orbits, they were suffering from round-off error, and they didn't know how to correct it. And so I had learned how to correct it in my scientific work. So I helped them do that so they no longer lose track of where the satellites are. They now can project for many years where they're going to be at any time of day. So, yeah, there's a lot of history there. I don't work with computers for a living anymore. By the way, just after I got my PhD in physics, I came up to the Washington area, and I was put on the Department of Defense Computer Steering Committee. And when I was working as a contractor for a while over in Crystal City, where they had all the admirals and everybody like that for the Navy and Air Force and stuff. And I demonstrated my computer for them. And they said, "How can this be? We're the inventors of the computer out at Los Alamos." And they said, We have spent billions and billions and billions of dollars on developing of computers, and you by yourself have made a computer that's 1,000,000 times as powerful as ours, or the best we made. They said, how can that be? And so I said, well, I'll bring one in and let you test it. So I brought it in and let them test it, and they couldn't believe it. I put one in their offices. They put 5,000 simultaneous users on it, and they couldn't slow it down. It was still faster than anything they had ever seen. And so that's sort of what happened. But again, the military did not like it because it didn't cost enough. $8,000 for a computer that capable was just. I mean, they were expecting to pay millions for each computer, and here selling for $8,000, and they really didn't care for that. And you see the stuff here: central processor management for CPM and NPM multiprocessor management. Those were some of the operating systems we put on the system, and I wrote them. The versions I did, I wrote them as a stack-oriented operating system, not a one that uses the RAM of the computer like operating systems do today. And so anyway, it was very interesting days.
Yeah, it's saying here that there's a changing marketplace with the introduction of the IBM PC. So how powerful was the IBM PC compared to your micro? Super micro.
Okay. The only one that was available when I first came out with my super micro was the IBM 1620. It was a 16-bit computer with something like 64 K of memory and a 16-bit processor. And my computer had petabytes of storage and ran 1 billion times faster. So they didn't compare at all.
Well, how did you have petabytes worth of storage? Because
I wrote all of this compression software. In other words, I wrote 52 compression algorithms. If you applied all 52, now, for instance, under Windows or CPM operating system that was put out by a lot of companies, when they put in data compression, they may give you a 2-to-1 or 3-to-1 compression ratio, but they only use one compression algorithm. I used 52, and so I was able to get the double or triple to the 52 power increase, and that was just tremendous. And so that's why I was able to get so much memory. But there were problems with that. For instance, NASA, when they got this space data coming down, they were putting it on tape drives, and tape drives lose their data after about a year or two. And so the NASA found they had to copy the tapes every couple of years or they would lose the data. And but they were using my computers in order to be able to get enough data on the tape. And the tape drives were very poor in those days in that they, if you were using a 16 bit processor like an IBM 1620 to write to tape. The 1620, it wasn't just 16 bits, it was 20 bits. You had 4 extra bits to help correct errors in the data due to cosmic rays. And so you had a lot of different types of technologies going around and different things like that. And So yeah, it was only after I left the NOAA and the Census Bureau that they started using some of these other machines that you see here. But everyone who's in the business hated it, except for the people who wanted more capable machines. Some people, like we used to have what's called the Federal Expo, and also NIST would hold meetings. People would come from around the world and to learn about computers. And when I went to these meetings, they would reserve for us a auditorium that would hold between 500 and 2,000 people. And often I would be scheduled to speak next to someone, and occasionally it would be someone like Bill Gates or Steve Jobs, but they'd only get a small handful of people, and I have my room completely full, the aisles completely full, the doors open, and people in the hallway trying to be able to see what they could get. And the news media, they were just all over the place. And so as they saw what computers could do. For instance, when I was at NOAA, we had the first computer that you could use your landline to call and talk to the computer and tell it what you wanted, and it would translate your voice into commands for the computer. And I mean, no one else had that. And that was just one of the things that, and this was in the 70s and 80s, you know. And so that was very different. And we also did the first bank transfer of funds, you know, electronically. Today we do that all the time. You can use your cell phone even and scan a check in and send it to the bank and get it deposited. But in those days, when we first did it, there wasn't anything like that. And so we used our modem card that we made, and the banks would transfer money between banks using the modem card. And the modem card that we did could do any baud rate up to a certain maximum. So let's say I wanted to use my baud rate as a security. So I would do it like my baud rate would do 30,103.2 baud. Well, nobody else had a modem that could do that. And so with this one, we could use just the baud rate as the security, and no one else. And if they could receive it, they didn't know what to make of it, just garbage. And so we did a lot of things with that technology.
So why is it that if you were able to do that compression, that wasn't later used in the PC industry? Because I remember, you know, we would have these compression things that could double the size of your little floppy disk. But, you know, if you could like make it 100 times more, that would have, of course, been better. So what happened?
Well, since I was working at the government, in the government at the time, I was not a contractor, I was an employee. I was not allowed to patent it or copyright it, but no one else could use it because it was done by the government. And so they were afraid they would be sued, so they didn't do it. And they still don't do it today. And one reason for that, I think, is there's much more money to be made if you don't use it.
Did you ever publish this algorithm anywhere?
The names of them and everything were published. IBM used to have a site where they had all my algorithms online, and you could learn a little bit about how to use it. Yeah, the whole thing was I was afraid I would be, and my wife and my family would be just annihilated or murdered if I did too much with this, because I've discovered the people in business, they didn't want it. They wanted to make big bucks, not small bucks. $8,000 for a computer that would replace 50 or 100 computers in a computer center. I mean, that's not going to make very much money for people, who are in that line of work. And also, I was very creative in writing financial software. My software was used in churches that were doing business in multiple states, and they had multiple ministries in the church, like maybe a deaf ministry, a missions ministry, a music ministry, a private school, and then the church itself. All those ministries and everything we're able to handle, and those were the most complex financial management systems. And so the system I wrote for the Census Bureau when I was there is still in use in the 16 bureaus of the Department of Commerce. But that's the NIST, Patent and Trademark, NOAA, Census.
I mean, they got like a 30-year-old computer in each of these data centers.
Well, at the time I left, they were in there. I'm sure they tried to get rid of them because they couldn't make money. And, the government is all about money for the employees, and I was very what do you say? I didn't know about all this stuff when I first started working, and I was too idealistic. And I since learned that even in ancient China in 3000 BC, everybody wanted to work for the government because of the kickbacks. And I didn't realize it's just been there for thousands of years. And so. Well,
I found this list of algorithms from IBM. Do any of these look familiar?
Yeah, I think these are the names that they gave them, but yeah, it's the same idea. Yeah.
But I don't think there's anything here that can do 53 times compression or anything like that.
Well, you have to use all of them simultaneously, not just one.
Because in my experience, if you take a zip file and you compress it again, it's not going to compress anymore, I suppose. But
well, the compression techniques are not quite the same as a zip file, but zip file compresses text, and I guess some things. Yeah. So, but these work on better on various types of data. That's why there's so many of them too, and so yeah. So there was a lot going on. We had what we called the CPM users group here in the Washington area. And in that group, we invented many, many things in the computer industry. And for instance, have you ever heard of DBase, the database system? That was invented. Have you ever heard of, all of the standard things like the Excel or Lotus 1-2-3? Those were a copy of a program that we invented here in the Washington area, and I used it in government agencies so that people in the financial department, when they received a bill to pay, they would go on their computer and it would show them all the bills they had paid to that particular company or for that particular thing, and they could see where this new one fit in and whether or not they should pay it. And then one thing I had on my dumb terminals is I had a scanner that was handheld, and we would make a template that would go on top of a bill, and you would just mark with a little window which things, pieces of data needed to be scanned and the order. in which they were scanned. And so you would just take this thing that was like a, well, a little bit smaller than a mouse, but it's, you know, you would go and scan each of these windows through the plastic template to pay the bill for, let's say, the electric company. And then you have another one for the telephone company. And then you have another one for gas and water and whatever else that you're paying through that financial office. And so I was able at NOAA, for instance, to reduce the number of people in the finance division from 150 some to 5. And they did a better job. And they produced all kinds of reports that could never have been produced in the past. But a lot of people didn't like that because, let's say you were a division chief or you were a branch chief. If there's only 5 people that's required to do that, you're not going to be a division chief. You're not going to be a branch chief, you know. And so you're not going to make $100,000 more. You just need someone who knows how to just run the scanner over the data as it comes in. And one person can do hundreds of bills per hour, no problem, maybe even 1,000. And so before they couldn't do that. They didn't have that kind of capability. So that's the kind of things that were happening. And we did many things. I worked on the first computers or printers, the first printers that would allow you to print not as a character, you know, like a typewriter, but with dots, you know, to make up the letters and the numbers and that sort of thing, and anything else you wanted to print. Matrix printers. Well, anyway, those were developed during this time. And and we needed that for people in Japan and China, Russia, who were using languages other than English, and they needed some way to be able to print their texts and their results and everything from their calculations. So that's what we made possible. And the first terminal in the world to ever do that, which was developed for me by Televideo, was the Model 950. And it also had a place to plug in your scanner in the back. And this is a dumb terminal. And you could load your character set to make your window, and you could put stuff in the window. And but we didn't call it Windows, but that's what we could do. And so I could have a calculator on part of my screen. I could have a spreadsheet on another part, and and I could have word processing on another part, and so I could have all these things going on simultaneously. And this is in the 70s, and so.
I thought that was all invented by Xerox PARC. You're saying you did it first?
Well, I don't know what date they have, but we did quite a bit in the Washington area, and one of the things we did is almost all the computers when I first started were card-based, and we wanted to be able to replace the card reader and the punch and everything with a dumb terminal. And so I had to write the software that would replace that. And the mainframe computer didn't know that I was doing this with a dumb terminal. All they knew is that it looked like it was what the input they were used to receiving from the card reader. And so it did a whole lot of stuff like that. And we had a group of about 500 people in the CPM users group here in the Washington area, and we had many creative people there. We developed so many standard, like the spreadsheet was developed there, the database was developed there, the modem card was developed there. Uh, all these type of technologies were done in this group. And what we did is we worked with one another. So let's say you learned how to do the spreadsheet and I learned how to do, let's say, database. So I would say, okay, I'll give you the source code for the spreadsheet and you give me your database source code. And we would trade. And that way, wherever you were working, you could use both packages. And so we did a lot of that. And we made rapid progress. So I wrote an awful lot of software that would handle all that kind of thing. And but I was recognized by NIST as one of the leaders in the world, and also at the Federal Expo and places like that. Those were handy and local. Until one day, the head of all computer systems at the Department of Commerce, which was over NOAA and NIST and NASA and all this other stuff, they were invited to speak at one of these conferences, and their room they were assigned to was next door to the room I was assigned to, and they noticed that they had about 50 people who came to hear them speak, and that my room was completely maxed out. And they said, that guy's under me. He works for underneath the Department of Commerce. And so they said, we don't want competition like that. So they said, don't let him speak at any more conferences, period. And then they came back to this person and said, well, we've already agreed that he's going to speak at these international conferences, and they're already, people are coming just to hear him speak, and we can't cancel that. We'll have to make it next year. And so they did that. So there's just a lot of things going on in the government. People felt like, well, I'm the most important person, and that person shouldn't be allowed to speak at a conference and have more people come than come to hear me. And so all those things are going on. And eventually, I had to leave and do something else. The last thing I worked in was computer security. And I wanted people to be able to work for the government from home on a telephone line with security. And I developed a security system that would enable that to be done. I used a contractor also in Leesburg, Virginia, to work with me. And so we demonstrated that, and we showed it was secure, and then we had to get approval from NIST and to use it. And NIST tested it, and they said, this is very secure, we can't break it. We do not allow any security system in the government, anywhere, that we cannot break. Therefore, we can't allow you to have this, because we need to be able to record everything that you're doing. And I pointed out to them that I have a software package that showed at the Census Bureau, where I was at the time, had on a typical day over 100 foreign users coming through their firewall and getting all kinds of personal information on the employees and stuff like that. And they were illegal. And none of the security systems that NIST had approved could stop them, but mine would. And they would not be used. So, when you see that sort of thing going on, it just makes you feel bad. If you're an idealistic person, you think, well, we don't want to pay all of our money to governments like this, and they just waste it and they give it to themselves. And so that's what's going on. And but the media doesn't really cover this, and they're involved in making money too. And so anyway, that's what's going on.
So you were involved in making the very first spreadsheets then? What was your involvement in that?
Well, in our CPM users group, we had a person who first did it. I'm trying to remember the name of it.
Now, they're saying here in this article, LandPAR, available in 1969, was the first electronic spreadsheet. And then the very, very first, most famous one was VisiCalc.
Yeah, VisiCalc. The Lotus 123 was the most lucrative spreadsheet program ever made, and it was basically stolen from the people that did it here in the Washington area. I can't right offhand. I'm having a senior moment. I can't remember all these details, but yeah. And so anyway, it's I'm out of the computer environment. I mean, I have computers at home, but I don't develop and market those computers anymore because the Micromation went out of business because of inability to understand international trade and when they're going to lose or make money, what the kind of contracts they have to write. And since the world's market is a lot bigger than the U.S. market, they ended up unfortunately losing money, and that's what caused them to go out of business.
I'm looking up the history of 123. So that was founded by Mitch Kapoor and originally written by Jonathan Sachs.
Yeah,
You're saying Jonathan Sachs basically stole the working software from your CPM users group.
Yeah. And you know, I hate to say this, but copyrights and patents and everything were not initially assigned to this field. So it was not I don't know how you say it. It was not
well, yeah, there was a lot of issues. I mean, I used to work for a company called Mosaic Software, and they created basically a clone of 123. You know, it basically did all the things, and Lotus sued the company, and along with Borland, who had also done the same thing. And I think they did eventually succeed, and there was all these look and feel lawsuits about that.
Yeah.
And now you can't even look and feel like another product.
Yeah.
Well, I guess back in the beginning, you're saying you could do whatever you want, right?
Yeah, that's pretty much what they did. And but then people, like for instance, if you were making a computer, like in my case, the Supermicro, well, no other computer had the same architecture as that. So the software that we put on it, even if you could steal it and take it over to another computer, it wouldn't necessarily work the same way because the hardware is different. And so that you just by making your hardware a little unique, you could avoid people just stealing your software, because they'd have to disassemble it somehow and get back to the source code and then rewrite it for the hardware they have. And that was often quite complicated, so they didn't bother. But
yeah, that is quite complicated. That's why nowadays we're still stuck with either the IBM computer or the Macintosh computers. But generally speaking, you only want to write your program for the big major computer users and not port it to every possible different computer.
Yeah.
We have Linux now, which is kind of universal, can kind of run on different hardware, although the primary hardware is still these days IBM Pc based or Macintosh based. But nowadays we write everything for the web now. So
Yeah, and you realize the web is just the bulletin board system that I, with a fellow from IBM, recreated, and he was in Chicago, and the bulletin board system was designed to run on telephone lines because we didn't have any internet in those days. But it did the same kind of function as the internet does with a website, and we created the software for banks. We created the software for self-government. We have the first place that had self-government done on the telephone line, where you could do it whenever you were available, and go to the bulletin board system that had your group that you were doing work for. And so, hey, well, I was interested in what Alistair was doing, and see, he has some computer background, but maybe not as intensive as this. But what got me into that was when I was working at the SREL, Space Radiation Effects Laboratory, and we had managed to get the designers of the accelerators that were at CERN at that time. It didn't work as well as they should have. We got them to try a second time, and this time they got it to work. And so it was 1,000 times faster. Then there was no way to record the data coming in at that rate, so we could understand what was happening in the experiments. And so that's why I had become involved initially in this area, because I needed a computer that was basically up to 1 million times faster than anything we had at that time. And so everything I heard of that gave an idea of what you might do to make it go faster, I worked with, and that was fairly successful. But I wasn't in the place to make money off of it. But when I was working for the government, I got the Micromation to agree that the government, U.S. government, could buy all the computers they wanted at $8,000 each, and they were buying them. And when if they had a problem, I would be sent out to wherever it was. I remember going to Spokane. I remember going to a lot of those western states where something would happen, and they would need someone to come and figure out what it was so they could get their system back up. And so I would sometimes go out and see that, and it was amazing. We use a lot of these computers in shipyards. In Spokane, I think that's where they have a big seaport. I think there's a big NOAA facility there where they repair ships and all that kind of stuff with thousands of employees, and they use it there too. So, yeah.
My
that's very interesting, Bill. Go ahead, Alistair.
My background wasn't in electronics. I was a programmer, and so I didn't build boards and such.
Right.
I made programs, but I used CP/M and WordStar when I first started. Then used HP 9000s. I loved them. They were great for a while with HP Basic, and we did a lot of our consulting work with different engineering companies and medical companies and such. That was a lot of fun. I learned so many different things from being so many different places. And then I worked for quite a few years for a newspaper company using DBase that you mentioned. I remember one particular task I did that you would appreciate. we had this one process. Each time there was a delivery of newspapers, there had to be a processing of where the flyers that were being inserted to each paper would go within like a city, because we had a bunch of different cities and towns. We ran about 60 different newspapers from this one system. And so within a town, you know, each grocery store only wants their flyers to go around where their grocery store is. And so all the flyers go to different routes. So when the vans are getting loaded up to take all the different stacks of newspaper sections and flyers, all of that has to be individually correlated. So that one process had to be run at the last minute once all the flyers were printed and everything. And it took quite a while. Sometimes with some of the larger distributions would take up to like 3 hours, and then they had to print out the run sheets that went with the delivery drivers based on the results. So if something went wrong with that process, then their drivers can't go out, their delivery boys don't get their papers, and the whole system falls apart. So that was a really super important process, and it took several hours. So what I did was I would take the data that we were going to work with for that day, extract it from the main tables, and then put it into a RAM disk, and did all the processing in a RAM disk instead of on the main tables, which were stored on the hard drives. And when we released that update for the programs, the difference in speed was so much that out of the 60 newspapers we distributed it to, we ended up with about 40 of the divisions calling us, telling us that the process was broken, it wasn't working, when in fact it was working. It was working so fast that they thought it was broken, because what took 3 hours was now down to maybe a minute and a half, because all the processing was being done in RAM and then put back into the tables on the hard drive instead of the processing being dependent on the hard drives. So that was like what you were saying about how you did all of the computations in the CPU memory, kind of a similar thing. It made it so much faster, but the users thought it was broken. We got all these people phoning up, I've tried it 5 times and it won't run. Well, what do you mean you tried it 5 times? Well, I press the button, and then like a minute later it says it's done. Well, did you go in and look and see if it actually is done? Well, no, it can't be done. That was too fast. That was so much fun. I felt so good about that. But so that was my D-base. But yeah, mostly I've been a programmer. Then I got into networking and then management and buying crap. And I'm a lot like you. I don't like to overspend for computer stuff. So I was a good IT manager because I would get good deals and keep costs down, reduce costs, as opposed to lots of people who run their budget up. I have one friend in the government, and he says that the motto is, if you have a budget, you use it or you lose it. So they would buy stuff just to use up their budget because they felt that the bigger their budget, the more power they had, or the more important they were. Whereas I was always the opposite. I was always trying to make my budget come down. But yeah, our backgrounds are very different. Yours sounds a lot more technically involved. But I certainly enjoyed being a computer guy, because when you're support within a company, you get to talk to everybody that has a computer you talk to. So you talk to guys in sales, you talk to guys in engineering, in CAD, in the machine shop, the shipping. You're a part of everything, and so you learn from all these different people. You learn things. You know, I learned about injection molding, about stamping, about just so many different things. I was really blessed that way. One of the things that I came across in manufacturing that helped me with my understanding of physics was called a vibrational feeder. And so basically it's this round drum, and it's got like a coil ramp up the outside of it. And then this drum gets vibrated, and then parts go up the ramp against gravity, because the vibration and the friction against the outside of the drum, it's kind of hard to explain. You'd have to see it. Maybe Franklin will bring up I'll see what I could find a good search term. They're amazing to watch.
What did you want to search for?
Vibrational feeder machine.
Vibrational feeder machine. Well, let's see what we got there.
There's a video that says Unite Automation Vibration Parts Feeder Handling Plastic. You see that video?
In what I'm sharing, let's see here. Let's see here. Let me share something first. Okay, so
go to videos.
Videos.
See that second
So what
one?
was it? This thing?
Yeah. And it's just one of the things I came across. You can turn down the volume. I don't think we're going to need it. And so what happens is, as it shakes, the parts go up the ramp. Nothing is pushing them. It's just the vibration and the shape of it. Pretty amazing.
So all that just to put it in, make it go into a box?
Well, the reason for it, I don't know exactly what they're doing there with it, but typically it's because you want it oriented a certain way.
Oh, okay.
So you're not just bringing it up the ramp, you're orienting it so that then, and where I worked for quite a few years at this place that built robotics, big assembly lines, maybe have like 100 robots in them, and they're all moving at once and welding and stuff. And so let's say you had a piece that had to get welded onto a car. They would come up in a feeder like this. A robot would be grabbing them one at a time, holding it in place and spot welding it. So see how it specifically is getting them to sit a certain way?
Yeah, I see that. It just like rejects any ones that are not pointing in the right direction.
And it's all just done with vibration. They're going upwards, because upwards is also outwards, and the vibration wants them to go outwards. So because of that, they make their journey upwards. They're pretty cool machines. And that's just a small example of the kind of stuff I've come across. Things that you know, a whole lot of people go through their life and never know exist. But just because of what I've done for a living, I've been exposed to a lot more things than the average guy.
So you're saying that that rim is not actually rotating; it's just vibrating.
Correct. Yeah, it's just a little motor on the bottom with an offset gear, you know, where the center of the gear, the gear is not, the axis of the gear is not at the center. So when it spins, it causes a vibration, shakes the whole drum, and then those things magically go up.
Yeah, that seems pretty magical. Like the laws of gravity have been repealed here.
Yeah. Yeah, when I first saw it, I was like, freaky. The one I saw was making washers go up. I'm like, what the heck? And you're looking at it and you're like, well, is there magnets or something? Like, why are they going up? It reminded me of liquid hydrogen when you supercool it. and then it starts dripping over the flask. You know what I'm talking about?
Yeah, that's superfluidity.
And it's with the case of the supercooled hydrogen, it's actually because the hydrogen is making a little march around the outside that is one atom thick. And so there's this one atom thick spiral of hydrogen going up the side of the glass till it gets to the top and starts to spill over. That's what that same concept is in both instances.
You think? I don't know. It's a little bit hard to tell it with the liquid helium here. Let's see. What are they showing here? They're showing everything but.
At first, when they did this, they thought it was dripping through the material, and then after they put a lot of attention on it, they found out it was coiling up the outside in such a thin layer they couldn't see it.
Yeah, the behavior of superfluids is something I'll often refer to when people say things like that if there was such a ether that it would resist movement and things like that,
Mm-hmm.
which is intuitively understandable, considering that that's what most mediums do. But if you can point at superfluidity and say, well, there are definitely some things there that you wouldn't think would happen. So I don't think we can just naively discount that or take for granted that things would have to be slowed in ether medium.
Nope. You and I are on the same page in that we both are convinced there's a ether, and I think Bill is too.
Well, no, Bill. His main idea is that the space is filled with actually the electromagnetic field, right? And that field is in fact fundamental, which is certainly a way you can start. But I would disagree that the physical explanation would be better served by starting off with particles.
Yes,
and that's been a big debate going on between us dissidents as to where you start, right? There's one camp that says basically that the waves are fundamental and that the particles are made out of these waves or wave energy or something but fundamentally the electron is made out of something. Versus those of us in the particle camp, which I'd probably say are fewer, who say that the particle is fundamental, like the electron is the fundamental particle that makes up everything. So those are two mutually incompatible trains of thought.
History has shown us that when there is a puzzle that has persevered, that it's usually the minority that ends up being right one way or the other. It's very seldom that the consensus gets it right in the first crack. Usually they come up with this mob think idea, and then along comes some dissidents and overthrow it. It's a pattern.
Yeah, that's generally what we hope for, I guess. That's what makes us dissidents, right? Okay. But I see we have Carl here, so since we do, I was working on answering your question to me. So I thought we would take a look at what was going on with the email. And no, just to give you guys a little idea of what I generally deal with on a daily basis, it's like these are like all the messages that I get on a daily basis from just this email list that I'm stuck on. So that's like maybe 20 messages a day. So Bill, I don't know how you handle your email where you get like hundreds of emails a day. I can barely keep up with just this little email list that we got going on here.
I'm 72,000 emails behind at the moment.
Yeah, I would just give up. I would just say, I don't know how you get anybody's messages. So
search for them.
But so since Carl's here, so I was going to be composing a message about the nature of polarization. So the way this discussion got started was that, let's see here, is that there was, once again, we're discussing this idea that that if there was a medium, that it would resist continuous uniform motion in a straight line, according to Newton's first law. So, so I was pointing out that, Newton's first law simply states that an object in motion actually encounters no resistance to a straight line. So I'm not quite sure that there's any real relevance here. I mean, how can you say that Newton's first law would resist continuous motion when it in fact says exactly the opposite thing? And then probably I said that probably he meant that probably Newton's third law, where every action has a reaction, must be coming into play, and that they think that any object moving through a particulate medium must be slowed down. And like I was saying, well, that's understandable. But then we got into some other things about the fundamental thing is about how waves gets transmitted. And the problem here is that if the medium is like this dielectric, then it must transmit waves just like sound would, right? It's really hard for it. I mean, even if light was this transverse thing, it would still have to be able to transmit a normal longitudinal wave. And I've always been saying for years that I have got absolutely no problem with that. I've been saying that the light wave and the radio wave is just like an ordinary sound wave for years, that you just have to figure out how this pesky polarization problem works, right? This is really the only reason why people think that the EM wave is transverse, and that it exhibits polarization, and somehow no one can figure out how to make polarization work if it isn't like a stupid rope through a picket fence explanation, right? So I provided the alternative answer that the polarization is actually mediated by the very large wavefront that runs perpendicular to the wave travel. And the example I give there is like the waves that you see come crashing on a beach. You can see the waves on approaching a beach are not like a rope-like object with like one tiny little spot. When the wave comes in, it comes in as a line, a very, very large line. So you can't think of a wave as like something like on a rope. What you've got to think about is a wave coming in this massive collection of matter, and it has this big wave front, and that wave front runs perpendicular to the wave travel. So you can see the wave coming towards the beach, but the direction if you are assigned at a vector direction, is actually perpendicular to that direction of travel. So, and certainly water is a particulate medium. And so all I'm saying is that in order to explain polarization, you first of all have to have some physical mechanism to encode the direction of polarization. So in the case of an ocean wave, you could have an ocean wave coming at you. This is the normal ocean wave that you would get. But you might also be having a wave that you could have running across at 90 degrees. So you have like a boat that's trying to go across the beach or something like that. Not exactly the best analogy, but you could have waves going the other direction. So you could see that there would be a way to represent the polarization of those waves. And you could think of it like if you had a ship in the middle of the ocean and you see a big gigantic wave coming at you, the ship captain knows that the worst place to be is to be parallel with those waves, because when those waves come and they all hit, the whole wavefront hits the side of the ship all at once, that's what's going to capsize you, because all the energy is able to exert its energy onto the ship all at exactly the same time. But the better thing to do is to take your ship and move it perpendicular to the wavefront. That way, you're only getting hit by just maybe the width of your ship is getting hit by this wave, and the rest of it passes by without losing any energy. So that is my explanation for how polarization can generally work in ordinary particulate matter systems, such as, for example, that was directly for waves. Now, if I can come up with that reasonable explanation, then because the only evidence that anybody has for transverse waveness is this polarization thing, and if polarization can be explained, then that completely removes, at least in my opinion, the whole logic for light or radio being a transverse phenomenon. And certainly it's not what mainstream shows, which an alternating magnetic and electric field. So some of the other emails are saying that, yeah, we've never observed an actual EM wave, and we most certainly have not observed the magnetic component of those waves. I mean, all this stuff is just on chalkboards. And I've asked people for, okay, show me the experiment that shows me the time-varying magnetic field from an EM wave. And you can pick any EM wave you want. And no one's really met that challenge, because and it's not like we can't do it. Just put a magnetic sensor in a line, and then you send a wave. You transmit a wave, and you should be able to detect the highs and lows of the moving magnetic field. And there's also articles being sent about other people who are speculating, how does the electromagnetic field move far away from any actual electric or magnetic source. Certainly at your transmission location, there's definitely an electrical effect going on. It may be a magnetic effect, but what's going on, a mile away where the wave is still detectable, but the transmitter, the atoms that cause the transmission are just way too far to ever be picked up. So that's the nature of the problem here. And Carl brings up the standard definition of the polarization of light, where if you have unpolarized light, it's directed through a plane polarizer, the resulting light will be plane polarized. Okay, so if it's directed through a second polarizer, both polarizers share the same orientation, all the light entering the second polarizer will pass through. Well, that isn't 100% true. All polarizers lose at least 50% of the light passing through them. But in any case, if the second polarizer is slowly rotated, the light exiting the second polarizer gets dimmer and dimmer and disappears when the axes become mutually perpendicular. The light reappears on further rotation and becomes brightest when the axes are again parallel to each other. This demonstrates that light waves are transverse. If light waves were longitudinal, they would never disappear, even if the orientations of the two polarizers were mutually perpendicular. So, of course, I would have a problem with that. I would say that this most definitely doesn't demonstrate that light waves are transverse. This does demonstrate that light has a component which is transverse, but that doesn't mean that light itself is transverse. And it's kind of difficult to even say what transverse light would actually mean, right? So that's another difficulty, in that light, you must be able to encode some kind of vector into light which runs transverse. Now the question is, can that be encoded in an ordinary longitudinal type wave? So I would say yes, that can. So I would go back and show, because this is a relatively recent idea that I came up with, which is the early polarization experiments. I think maybe Hertz did these. Let me see if we can find this here.
Franklin?
Yes,
So back to the second polarizer, you said that all polarizers basically get rid of 50% of the light.
Yeah, practical ones.
Yeah, and I would say in the case that I cited in the email you just read, that the first polarizer does just that. But because the second polarizer, if it's oriented in the same direction as the first one, there's no further effect. Because the point of a polarizer is to get rid of things that are in a different orientation, but all the light that comes through the first one is already in the same orientation that the second polarizer is angled at or aligned at. Therefore, there's no further effect. It doesn't reduce another 50%. That's why if you rotate it 90 degrees, the second one, that it all goes away. There you're getting rid of the other 50%. Does that make sense to you?
Well, my understanding was that one of the characteristics of polarizers is that they basically act like sunglasses, that they, no matter whether you've got polarized light coming through, that a significant fraction will get lost. Yeah,
through a first polarizer, yes.
And even through a second polarizer.
Yeah, this is the problem with, if you have unpolarized light going through a polarizer, yes, you're going to lose a lot of the light, because the polarizer itself is getting rid of all the portions of the unpolarized light that aren't in the right orientation. So yes, it's dimmer. But if you shine it through a second polarizer of light that's already polarized in the same orientation that the second polarizer is set up in, there's no further loss, because it's already in the same way it's going to filter it anyway.
I'm trying to look through, trying to find the reference, but I think that most standard like polarizers, even if oriented in the same direction, will lose a significant amount of light. And that's kind of a problem with the way LED screens work, because I have to go through at least 2 of these polarizers, and at each stage it loses a significant amount of light. Although I don't want to get into that in particular. That's not really relevant to the discussion here. So that's more of a practical problem than, I don't know, a theoretical one. If you get really, really expensive wire grid polarizers, those may in fact be transparent. That from a practical standpoint, it's probably more of a manufacturing thing than anything else. But you might want to take a look at that, which is the transmissive percentage for a polarizer for just like, any light at all.
I have a question for James. I see he's on the call. James, are
Hello.
you? Hello there.
Hello. Hi, I'm here.
Hey, I had asked Franklin for your email address after last week's call, and he gave it to me. And I sent you an email, probably late Sunday night or something. And I don't know that if you received it.
Let's see, Sunday night. That would be almost a week ago.
Yeah. So maybe Monday morning for you. I don't, like real
Well,
early days.
no, I did not receive it. But believe it or not, Franklin very considerately sent a copy of his reply to you with my email address, which, by the way, for everybody, is jamesjkeen@gmail. And so please, sir, could you send that again?
Okay. And perhaps I didn't get any error message back, like I addressed it wrong or anything. So,
oh, well, that is strange because usually everybody that sends me an email, I do receive it.
Perhaps it's like directed to your spam folder or something. But I will go ahead and resend it again. So I'm curious. I have a question in there for you that, based on last week's chat, what you were talking about with the lunar ranging data.
Well, I'm going to give a second email address. KeenJ@cwdom.dm. That's KEENEJ @cwdom.dm.
Okay,
and so that's my second email address. And so if you just send a copy to that, I can check, because maybe some strange things have been going on in terms of, well, for one thing, I never go to Gmail. I use the Thunderbird, Mozilla Thunderbird client, and that takes care of downloading my emails. So I have a hard copy.
I would explain it. Hang on a sec.
Okay, well, hopefully we get that straightened out.
Okay.
But I finally dug up the picture here so I can answer Carl's question.
Oh, good.
Which is, how can this work? Now, I'm not exactly sure that this exactly applies to light. So, but I will say that I can see how this works in, say, radio waves. All right? So, and light and radio waves might fundamentally be different. But to answer Carl's question, which is how can this work if the waves are longitudinal? So we have this picture here, and on, say, the right side, we have a transmitter, and that's just two wires which are oriented vertically, right? Now, what I'm saying is that the wave that gets transmitted out of there is a ordinary longitudinal wave, but it is shaped like the transmitter. So you can imagine that if there was water around those vertical bars, and the vertical bars were just like literally expanding and contracting like they were a balloon, that they would create a wave which has a very, very large vertical component to it. Right? Can you imagine that? Because you have to be able to imagine that the wave that comes out, like this was in a wave tank, the wave that would be coming out would have the original shape of the original transmitting transmitter, and that would once again just be ordinary longitudinal wave. There's nothing transverse in there, and it's an ordinary compression wave. So now the deal is that is like the wave like crashing on the beach. Okay. Now what we have in the middle here is what is called a wire grid polarizer, and all this is just a series of wires strung across a frame. Now the deal is that, like in the orientation A, that orientation, which is perpendicular to the transmitter, that is actually the blocking orientation. No, actually, no, that's wrong. That is actually the orientation that allows the wave to pass through, right? So if the grid polarizer is at 90 degrees to the transmitter, that allows all the wave to travel through, which is a bit counterintuitive. Now, on below B, where you have the grid polarizer, so it's actually parallel to the transmitter, that actually absorbs all of the signal. So it can't. So you don't receive anything at the receiver in B versus A. So the question is, how does that work? Now, if you're imagining that the waves are like the ocean waves, then if your grid is aligned exactly the same way as your transmitter, that's a bit like the ship sitting broadside to the wave. So as the wave comes, it will hit the entire height of that wire all at once. And this is what they would call, basically, is an absorption polarizer, and this is how they theoretically think that these wire grid polarizers work. And it actually, because the wave comes in and hits the wires all at once, that it actually generates electricity. And that actually causes a slight current to flow in the wire, and you would actually observe some heating going on because the wires are actually absorbing the radio waves, and then because they're absorbed, they're not allowed to proceed to the other side. So, but that is a very basic and important concept to understand in order to accept that a longitudinal wave can get absorbed upon these wires, like the ship taking the broadside of a wave. And that is how the actual polarizer works. Now, if you look at the top, when you orient it 90 degrees, now this is more like orienting your ship 90 degrees to face the incoming wave. I mean, it's a little bit harder to imagine, but when the wave front hits the wire, basically it's only going to intercept just basically the width of the wire, pretty much. But certainly it's going to be different than if it's oriented straight up and down, where it will obviously absorb the entire energy of the wave all at once. So when it's oriented the other way, then it can really only, when the wave front hits, it's only going to hit a little tiny piece of every single wire that's oriented in the wrong direction. I mean, it'll absorb some, but it's not going to be anything like what's in the bottom there. So
okay, so one thing about this, your question in your original email had to do with waves crashing on the shore, which are definitely longitudinal. What you're discussing now are ocean swells out at sea affecting ships. Those are transverse waves.
Well, they are, but they are still mediated on a particulate medium.
Yeah, they are. That is true.
But that is being used in the way of an analogy. But what's important about the analogy is that crest represents a region of compression, rather than a region of I don't know. In the case of ocean waves, that's where it's really literally built up, right? So there's definitely more matter in where the wave is cresting, but it's just a matter of compression and identifying where that compression is. So I think it's still a fair analogy to say that if you have your transmitter, and like I said, if it was like totally, say, underwater, and maybe you attach it, like say a speaker type device to a vertical pole that's in the water, and you vibrate it back and forth, that the wave, that you'll get waves there. Those aren't, then that case is definitely not transverse wave, right? That would have to be an ordinary longitudinal compression wave. So that would create pressure. And what I'm asking you to imagine is that if you had another pole in the water and it was oriented in the same direction as your transmitter pole, that when the wave comes, it's going to hit the full length of the pole all at the same time. Now, if you take that same pole and you oriented it 90 degrees, then the whole wave will eventually hit the pole, but it's gonna when it hits, it's gonna, the wave is going to be curved somewhat. There's always going to be some curvature. That it's not going to hit the entire width of the pole at the same time, right? At most, it's going to hit it at some delay. But that is kind of my answer to your question, which is, how does the polarizer work? Now, your specific question was starting with unpolarized light. Okay, so, but once you get it past the first polarizer, then you're dealing with this situation here, which is that you put it through another polarizer. As you rotate the polarizer, then that is just a geometric, because everything always has vectors. There's always going to be an up and a down vector. I mean, an X and a Y vector kind of thing. And there'll always be vector parts which are allowed to go through until you completely orient it at the 90 degrees where there's nothing left to transmit that's in the correct vector direction. But I like this explanation because it gives you a more of an actual physical idea of what is actually going on in the polarizer. And I think you have to kind of understand that it's basically a sort of electrical receiver. And this is why when you're transmitting a radio wave, that it works better if your transmitter and your receiver antenna look the same. So if you're transmitting with a vertical rod, then you better have a vertical rod as a receiver. If you have a vertical rod as your transmitter and a horizontal rod as a receiver, that's not going to work so well. And it's all just this physical picture that you can see just with compression waves coming through, rather than this whole kind of muddied explanation about how a wave could be transverse. And I was pointed out earlier, transverse waves can really only exist in the boundaries between different things like air and water. It's really the only place you can really get a transverse wave. And then what would that correspond to in space, right? What would be the boundary of anything? I mean, there is no boundary of anything. So I don't even think that transverse wave makes any physical sense at all. So, Carl, what do you think of that?
I might go ahead and send you a description using ocean water, since that's how we've framed this, or the discussion we're in today, that might make sense to you. But my reply, my original email reply, was regarding the crashing wave on the shore. And you've gone away from that out to ocean swells. It's a different thing. I agree with you that crashing on a shore are definitely longitudinal because the water's actually moving inward into the land. And the swells are not, they're transverse, they act differently. The water's not really moving, it's the energy of the wave that's moving. Anyway, different scenarios. And so that's what I was asking you is, okay, explain how the ones crashing on the shore don't violate this principle that I pointed to in the email. But I'll give you an example in the email. I'll write it up because hopefully it'll make sense. It's kind of lengthy. One more thing. James did have his flag up there momentarily, but I'd like him to repeat that other email address if he would, so I can send him this email again. I didn't quite get it down right.
Sure. It's Keen J, KEENEJ, at CWDOM.DM.
Okay, I got it.
Okay, I look forward to hearing from you, sir.
All right, thank you.
Okay, Carl, well, I'm not quite sure I still understand the nature of your objection. I'm just trying to explain that the only thing you need to do is actually just figure out how to get a transverse component encoded upon a longitudinal wave. Now, how it gets received and how it gets decoded.
Wait a minute, why is it my responsible to figure out how to get a transfer component onto a longitudinal wave? Why isn't that your responsibility?
No, that is my responsibility. That's what I'm trying to explain. I'm trying to explain that's what I'm doing. I'm saying take ordinary longitudinal type wave, like sound wave, encode a shape onto it that contains the transverse component, and I feel that is sufficient to explain how that happens and how the radio wave can be encoded on ordinary longitudinal media. So that would be my point, rather than coming up with these, the mainstream idea that there's this varying electric and magnetic components that are 90 degrees to each other. That I just don't see. And that there's actually nothing, it's grossly misnamed, in my opinion, the electromagnetic wave, which actually doesn't contain any electric or magnetic components in it at all. I just see it as an ordinary compression wave. And when the compression wave hits receivers, like the metals of an antenna, that is just causing the electrons within the metal to wave in sympathy with the incoming wave. Just like if they have like these ocean generators that they can generate electricity from the incoming waves because they just makes them go up and down. It's a physical thing, and then we just amplify that the signal that we get from the electrons being literally impressed into the surface of the metal as a signal, and the reverse is true for when you're transmitting, which is that you're just sending a voltage into your metal, and that is causing the electrons to literally poke out of the surface of the metal, and that creates a higher pressure in the space, which is what actually gets transmitted. That compression wave is what's actually getting transmitted. There's no electrical field being transmitted. There's no magnetic field being transmitted. All it's doing is transmitting a compression, just like sound, which is what I've been arguing for. So just have to figure out this polarization thing, which admittedly, that's still kind of loosey-goosey and all that, but it's what I'm working with. So, but it looks like we're at the end of the time today, and so I'll thank Bill Lucas. We had a very interesting history lesson about how he invented most everything we use today, apparently, in the field of computing. And then we got a little bit into the interesting story that Alistair had about what happens when you speed up a process like 100 times. And that's always fun. And then we got into some of the emails about the nature of space, whether particles are fundamental or whether waves are fundamental or whether fields are fundamental, and particularly into the nature of how polarization works as a ordinary compression wave phenomenon. But so thanks everyone for coming today and participating. And that will do it for this week's episode.